Hello and welcome to this lecture series on ordinary differential equations. In the first lecture, we are going to talk about the definition of ordinary differential equation and the formulation of ordinary differential equation. The definition of ordinary differential equation: a differential equation containing one or more functions of one independent variable and the derivative of those functions is an ordinary differential equation. Okay. So the word says ordinary differential equation. So one thing is that it should be a differential equation, so equality sign should be there, a derivative term should be there, and ordinary means that derivative is only with respect to a single independent variable. Okay, say for example dy by dx is equal to 2. Okay, so it is an equation with a derivative term where derivative is dy by dx, and it is ordinary because the independent variable is only one. Okay, there are two variables in this equation, y and x. Okay, the y is the dependent variable and x is the independent variable. So independent variables are those with which we differentiate. Okay, and dependent variables are the variables which are being differentiated. So if we are writing dy by dx, that means y is dependent variable of x and x is the independent variable. So this is a ordinary differential equation because the independent variable is 1. It's a equation containing derivatives. Say I take another example, say dy by dx is equal to 3x square. So again it's a differential equation because the derivative term is there, equality sign is there, and it is ordinary because the independent variable is only one, which is x. Again I take another example here, dy by dx is equal to x plus sine of x. Okay, so x is the independent variable because we are differentiating with x, y is the dependent variable, and so this term is dy by dx is the derivative term and there is the equality. Okay, so again it is a ordinary differential equation. Another example, d2y by dx square plus 5 dy by dx is equal to cosine of x. So again right hand side is a function of x. On the left hand side there are two derivative terms, dy by dx, first derivative term y dependent, x independent, and similarly there is another derivative term which is again second derivative of y with respect to x square. So again x is the independent variable and y is the dependent. So in this whole equation y is dependent variable, x is the independent variable, so there is only one independent variable, derivative term is there, equality is there, so it's a differential equation and it is ordinary differential equation. Say I take another example, d3y by dx cube minus 4 d2y by dx square plus 5 dy by dx plus y is equal to e raised to power 2 times x. So again it's a ordinary differential equation where you have a third derivative term minus 4 times second derivative term plus 5 times first derivative term plus y is equal to exponential function of x. Okay, so independent variable is just one, we are differentiating in each term wherever there is derivative is with respect to x only. Take another example, y dy by dx is equal to 1. Okay, so again it's a differential equation and it is ordinary because derivative is only with respect to one variable. Okay, and there is a derivative term present in this equation. The seventh example, d2y by dx square plus 5 dy by dx whole square is equal to x. Okay, so again derivative here is with x, here also with x, and there is a simple polynomial term. So this equation is ordinary differential equation. Okay, ey dy by dx is equal to e power x. Okay, so they are exponential functions but the derivative term is dy by dx. So y is dependent variable, x is independent, and so it is a ordinary differential equation. Y dy is equal to x dx. Okay, so now it is not written as dy by dx. Okay, but you can easily write this by taking dx on the other side. We can write y dy by dx is equal to x. Okay, so if I divide with dx, then y becomes dependent variable and x becomes independent, and it's a ordinary differential equation. If I divide with dy, then I can write it as y is equal to x dx by dy. Then in that case x becomes the dependent variable and y becomes the independent variable. But in either case there is only one independent variable, so the differential equation remains ordinary either in y as dependent variable or x as dependent variable. Okay, and say one last example, du by dx plus v is equal to cosine of x, comma dv by dx plus u is equal to sine of x. So now here differentiation is u with x, so x is definitely independent here and u is the dependent. Okay, v not clear from here, but if we see second equation, then derivative is v with respect to x, so x is independent and v is dependent. Okay, so these two equations are simultaneous equations with one independent variable which is x. We are differentiating with x here and also here, and u and v, they are two dependent variables. That's why we are saying one or more functions of one independent variable. So there are two functions u and v, and both are functions of one independent variable x. Okay, so it's a system of ordinary differential equations. Okay, now how we can differentiate different differential equations. Okay, so we can differentiate by knowing what is the order and degree of differential equation, whether the differential equation is linear or non-linear. Okay, so first definition is what is the order of a differential equation. The order of a differential equation is the order of the highest derivative which occurs. Okay, so if you are given a differential equation, it must be having derivative terms. Okay, so what is the highest derivative present in the equation, that will tell us the order of the differential equation. And second is the degree of a differential equation. So the degree of a differential equation is the power of the highest order derivative which occurs. So once we know the order from the highest derivative, what is the power of that highest derivative, that will tell us the degree of the differential equation. For example, say you are given this simple equation dy by dx is equal to 2. So it's a ordinary differential equation, y dependent variable, x independent variable. Okay, so where are the derivative terms? So it has only one derivative term, this dy by dx. Okay, so that's a first derivative term. Okay, so order becomes 1. Okay, because derivative is first derivative. Okay, so it gives the order 1, and this dy by dx term, it has a power of 1. Okay, dy by dx whole power 1, so that tells us that the degree is also 1. So I take another example, d3y by dx cube minus 4 d2y by dx square plus 5 dy by dx plus y is equal to e power 2 times x. So it's a differential equation which is ordinary, y is the dependent variable, x is the independent variable. Now we have to find where is the highest derivative term. Okay, this is a exponential function in independent variable. This is a dependent variable y, the first derivative term, here the second derivative term, here the third derivative term. So highest derivative is this third derivative d3y by dx cube. So it immediately tells us that the order of this differential equation is 3. Okay, so order becomes 3, and degree is the power of this term d3y by dx cube, its whole power is 1. Okay, so degree is 1. So order of this differential equation is 3 because there is a third derivative term is the highest derivative, and degree is 1 because this term has a power of 1. Okay, say I take another example, d2y by dx square plus 5 dy by dx whole square is equal to x. Okay, so now we have a first derivative term and second derivative term. So highest derivative is second derivative, so order becomes 2. Okay, and what is the power of derivative? Here power is 2, here power is 1. Okay, but degree do not depend on the highest power, degree depends on the power of highest derivative. So highest derivative is d2y by dx square, its power is 1. Okay, so degree remains 1. So order is 2 and degree is 1. Order 2 because second derivative term is the highest derivative term, and the power of this term is 1. Okay, so that's degree. Take say one more example. 1 plus dy by dx whole square whole cube is equal to d2y by dx square whole square. Okay, so find out the highest derivative. Okay, the constant number, dy by dx is first derivative, d2y by dx square is the second derivative term. So second derivative term is the highest derivative term, so order becomes 2, and the power of this term is 2, so degree is also 2. Okay, so order is 2, degree is 2. So this way we can check the order and degree of a differential equation. The second thing is the linearity, whether the differential equation is linear or non-linear. So an nth order ordinary differential equation in dependent variable y is said to be linear in y if these three conditions are satisfied. Okay, so linearity and non-linearity, it depends on the dependent variable. Okay, so if you have dependent variable y, then differential equation will be linear in y if dependent variable y and all its derivatives are of degree 1. Okay, so wherever y is, the power of y is 1. Wherever derivative is there, dy by dx is there, its power is 1. If the second derivative is there, d2y by dx square, its power is 1. Okay, so degree has to be 1. No product term of y and or any of its derivatives are present. Okay, so wherever is the dependent variable, it should not be multiplied with its derivatives, and also the derivative terms must not be multiplied together. Okay, no transcendental functions of y and or its derivative occur. Okay, so there is no transcendental function of dependent variable or its derivative. Transcendental function mean the trigonometric sine cos functions or exponential functions or logarithmic functions, etc. Okay, if any one of the condition is not satisfied, okay, then the differential equation is non-linear. Okay, say for example, dy by dx is equal to 2. Okay, so there are two terms in this differential equation. One side dy by dx, other is 2. This is a constant number, and dy by dx dependent variable is y, which is occurring only one time in this equation. Okay, so this differential equation is linear. The dependent variable has degree 1. Okay, the y power is 1. Dependent variable is not multiplied with dependent variable, so this y is not multiplied with any other y. Okay, and there is no transcendental function of y. Okay, so this differential equation is linear. So take another example, d3y by dx cube minus 4 d2y by dx square plus 5 dy by dx plus y is equal to sine x. Okay, so there is a sine function here, but this sine function is of only x, and x is a independent variable, not a dependent variable. Not dependent variable is y. Okay, so sine x function here does not impact the linearity or non-linearity, because linearity depends on dependent variable. So the first term is this, here y occurs only one time. Okay, second term is this, y occurs only one time. Third term is this, y occurs only one time, dy by dx. Fourth is this, y is again one time, no power, no multiplied with dependent variable, and right hand side is definitely not a function of dependent variable. So this whole differential equation, which is third order first degree, is a linear differential equation. Okay, it's a linear differential equation. So take another example, d2y by dx square plus 5 dy by dx whole square is equal to x. Okay, second order first degree ordinary differential equation with dependent variable y and independent variable x. The first term y occurs only one time, the last term independent variable, but this term dy by dx whole power 2. Okay, so that this derivative term is multiplied or is squared. Okay, so because of this term, it can be written as dy by dx into dy by dx, so y is multiplied with y. Okay, the derivative term is multiplied with the derivative term, so this equation is a non-linear differential equation, because the second condition do not satisfy or the first condition do not satisfy. Derivatives are not of degree 1. Okay, first derivative is of degree 2. Take fourth example, 1 plus dy by dx square whole cube d2y by dx square whole square. So again non-linear equation because second derivative term has a power 2. Okay, the differential equation is not of degree 1, it is a degree 2 differential equation, non-linear. Okay, okay, this one example. Okay, y square dx plus 3xy minus 1 dy is equal to 0. Okay, so now this is a differential equation either in y or x depending upon whether I divide with dy or with dx. If I divide with dx, it's a differential equation with dependent variable y. If I divide with dy, then it will be a differential equation with dependent variable x. Okay, so if I divide with dx, then it will be y square plus this times dy by dx is equal to 0, and y will be the dependent variable and you have y square term. Okay, so the first condition will not be satisfied, so it becomes a non-linear equation if y is the dependent variable. On other side, if I divide with y dy and write this as y square dx by dy plus 3xy minus 1 is equal to 0, then x is the dependent variable, and in this term there will be only one x, here only one x, here only constant number. Okay, so it will be a linear differential equation in x. Okay, so this is a differential equation which is a non-linear differential equation in y and linear differential equation in x. Okay, so depending upon whether you make the dependent variable as y or x, equation can be linear or non-linear. Okay, but in either case it is a ordinary differential equation. Okay, because if you divide with this, y becomes the only independent variable. If you divide with dx, x becomes the only independent variable. Okay, now how to formulate an ordinary differential equation. Okay, so an ordinary differential equation is formed by elimination of arbitrary constants from a relation in the variables and constants. Okay, so if you are given any equation in variables and constants, say for example you are given y is equal to ax, where x is variable, y is variable, and a is a constant. Okay, and a is a arbitrary constant. Okay, arbitrary number. So what is this? This is a equation of straight lines. Okay, so it's a equation of straight lines passing through the origin. Okay, so we call it a family of straight lines passing through origin where a is arbitrary number. Okay, and it's a one variable. Okay, family. Okay, there is a one constant. So how to formulate a differential equation for family of straight lines passing through origin for this equation? Okay, so what we have to do is formulate a differential equation. So what we will do is we choose one as independent variable, one as a dependent variable. Say x is the independent variable and y is the dependent variable. So we will differentiate this equation with respect to x. Okay, so your first step is that you differentiate this with respect to x. So left hand side becomes dy by dx. Okay, and right hand side becomes a, because the derivative of x with x is 1 and a is a constant. Okay, now you have two equations, the original equation and one derivative equation, and a is a arbitrary constant. This a can be eliminated. Okay, so what it says is differential equation is found by elimination of arbitrary constant, and here arbitrary constant is a, so we'll eliminate a from these two equations. For elimination of one constant, two equations are sufficient. So if we substitute a value from here in this equation, then the differential equation becomes dy by dx as y by x. Okay, so it's a, you can see it's a differential equation, y as dependent variable, x as independent variable, the highest derivative is dy by dx, so it's a first order differential equation, its power is 1, so it's a first degree, and the first term here, y dependent variable, is not multiplied with itself. Here also it is occurring only one time, so it's a linear differential equation. Okay, so formulation of differential equation is very simple. If you are given any equation, you need to eliminate the arbitrary constants, and say to eliminate one arbitrary constant, you can differentiate it one time and then eliminate the constant. If you have more than one arbitrary constant, say you have two arbitrary constants here, a and b, equation is y is equal to ax cube plus bx square, then to eliminate two constants, one derivative term equation and this equation, two equations are not sufficient. To eliminate two constants you need at least three equations. Okay, so we will differentiate this equation two times with respect to x. So let us first differentiate this one time with respect to x. So left hand side is dy by dx is equal to 3ax square plus 2bx, okay, on taking derivative. Again differentiating this with respect to x. So this left hand side becomes second derivative, this becomes 6ax, this becomes plus 2 times b. So now you have three equations and two constants. So you can eliminate these two constants a and b, and that will give us a differential equation. Okay, so on eliminating a and b from these three equations, you can get a differential equation which is ordinary differential equation. Okay, so I have not solved it here. You can solve simple three equations. You can eliminate these two constants a and b. Okay, so here uh, the highest derivative is d2y by dx square, so second order, its whole power is 1, so first degree. And in this first term there is y occurring only one time, dependent variable. In this second term y occurring only one time, and in this third y occurring one time. Okay, so it's a linear differential equation. So what we learned is if you have only one arbitrary constant, then it will end up with a first order differential equation, because we are going to differentiate it only one time. Okay, if you have two arbitrary constants, we will end up with a second order differential equation, and because we are going to differentiate it only two times. Okay, so the uh, order of the differential equation is immediately known from the given equation, depending upon how many arbitrary constants are there. Say I take another example here. Say form the differential equation from the equation x y is equal to a e power x plus b e power minus x. Okay, so if you look at this equation, there are two arbitrary constants a and b. Okay, so without solving we know that it will end up in a second order differential equation. Okay, order is known. Okay, degree we do not know. Okay, what degree we are going to get, and linearity we do not know. Okay, but order is known. Okay, so let us solve this. We have to differentiate this equation two times. Okay, so given this equation, differentiate it one time with respect to x. So apply product rule on left hand side, y derivative of x plus x derivative y. Okay, on the right hand side a e power x and minus b e power minus x. Okay, again differentiate this with respect to x. So y derivative with x, that comes here, and again product rule here. So x second derivative plus first derivative, which is, so these two terms add to write two times dy by dx, a e power x from here, and this becomes again plus as minus sign goes outside, so plus b e power minus x. So again we have three equations and we have to eliminate a and b. So now you see that in the third equation right hand side and the first equation right hand side is same, so I can substitute this value as xy here. That will eliminate both constants a and b. Okay, so the differential equation by eliminating a and b from first and third equation will give this. Okay, so it's a second order first degree and again a linear differential equation. So I took this example just to show you that we have to differentiate this two times, but it is not required to eliminate constant using all the equation. Sometimes few number of equations can help in eliminating all the constants. Okay, so you can use this fact also. One more example is that find the differential equation of a family of the circles passing through the origin and having center on the x-axis. Okay, so now in this case the equation is also not given, but you are given that the equation is the family of circles passing through the origin and having center on the x-axis. Okay, so you can take x and y axis and take center on the x-axis at h0, and the circle is passing through the origin, so the radius also becomes h. And so you can write the uh, equation for this family of circle passing through origin as x square plus y square minus 2hx is equal to 0. Okay, so now in this equation there is only one arbitrary constant, which is h, so we have to eliminate h. So we will differentiate this equation one time only. Okay, so differentiating this with respect to x one time, so it will give 2 times x plus 2y dy by dx, that's and minus 2h is equal to 0. From here we can calculate h easily. Okay, so we can substitute h value here and that will give us the differential equation. So immediately on substitution we end up with this differential equation which is ordinary but non-linear, okay, because y square is there, also y multiplied with y in the first term. So because of this and this both terms they are non-linear, so this is a first order first degree non-linear differential equation. Okay, so this is about how to formulate the ordinary differential equation. Now if you are given a differential equation, how what is the solution of a differential equation? Okay, so a solution of a differential equation is a relation free from derivatives between the variable which satisfies the given differential equation. So if you are given a differential equation, then solution will be called a equation which is free from derivative, and that equation must also satisfy the differential equation. For example, the differential equation dy by dx is cos x, it has a solution y is equal to sin x plus c, because this equation is free from derivatives and it satisfies this. If I take the derivative of this equation with respect to x, then dy by dx is equal to cos of x. So this is a solution of this. Okay, so what type of solutions do we have? Okay, so we say that we have two types of solution, one we call the general solution and one other is called the particular solution. Okay, so the general solution of a differential equation, the general or complete solution of a differential equation is that in which the number of independent arbitrary constants is equal to the order of differential equation. Okay, so we call a solution to be the general or complete solution if the number of arbitrary constants equals the order of differential equation. So in the previous, now we formulated differential equation from the equation. Okay, and we know that if you are given any equation, then the order will depend on how many constants are present. Okay, similarly now the solution will be general solution. Say if you are given first order differential equation, then if the solution has only one arbitrary constant, it is a general solution. If we do not have arbitrary constant here, okay, if y is equal to sin x is the only solution without c, then it is not a general solution. Okay, it must have the same number of independent arbitrary constants. Okay, the other type of solution is called the particular solution. A particular solution is that which can be obtained from its general solution by giving particular values to the arbitrary constants. Again, say dy by dx is cos x. This is a differential equation. It has solution y is equal to sin x, y is equal to sin x plus 1, y is equal to sin x minus 1 by 3, and so on. There can be many other. By using c value 0, c value 1, c value minus 1 by 3, by giving particular value to the arbitrary constants, we can write the particular solutions to the differential equation. Okay, so if a differential equation has a solution and in that solution the number of independent arbitrary constants are same as the order, then it becomes a general solution. If the number of arbitrary constants are less than the order, then we call it the solution as a particular solution. Okay, so this is about the solution of differential equation. It can be general or particular, but then how to find out these solutions for the differential equation? If you are given any differential equation, how to calculate the solution of a differential equation? So that topic is not simple, but we'll start by taking the first order first degree differential equations first, and then we will slowly move to higher order differential equations. So in the next lecture we will talk about first order first degree ordinary differential equations, and then we'll see how to calculate solutions of first order ordinary differential equations. Have a good day.